Welcome to the first talk of this track. Next up is Andres Leu, who will talk about deriving via.
Okay, yeah, welcome. So I should first say that even though it's me speaking today, it's really a lot of the credit goes to Baldur, who is perhaps in the audience, I don't know, yeah, and to Ryan, so this wouldn't happen without them. And yeah, so I don't know about you, but I mean, even though I would consider myself a programmer, I'm actually more happy if I don't have to write programs. So if I have a data type in Haskell, right, this is a simple one, and I, for example, want an equality function, then I'm in luck, right? So I can just write something like this, and that's it. And there's a really good chance that this equality function is actually the one that I want. So that's nice, right? So this is something that I think we're all using. And in fact, for a data type like this, I can even go on and I can derive all sorts of things. And it just happens, and it just does the right thing. It's ideal situation, okay? But there is a limited amount of classes for which this works. Now, this is a problem that has already been solved to a large degree, because if you now come to other classes that are not sort of supported by GHC directly, let's, for example, say something like from JSON or to JSON, you might still be in luck, because you can do something like this. You can derive one magic extra class, generic, and then you can simply derive these as well. Right? So this works a little bit differently in the sense that for the first line, it's all in GHC, right? But for the second and the third line, so how to derive generic is actually within GHC, but how to derive from JSON and to JSON is actually described in the ASOM package, and there is a definition for it, okay? But of course, I mean, it's quite nice if people can give these definitions, but even in a situation like this, it's not always clear whether we get really what we want. So for very, very basic classes, you might be able to argue that most of the time what you get derived by EQ or ORD or show is actually what you want. But even by show, it's already, so for example, I'm often annoyed by the fact that if I have a record data type, then the show instance includes all the record field names. So, I mean, that's understandable that it does, but often it just clutters up like very simple values, right? So even there you might, sometimes you might want to have something slightly different, but we'll get back to this question in the end of the talk. But now, what if you want to, for example, derive a semigroup or even a monoid instance for this data type? There isn't one in the libraries. I mean, so it's not like you can just write deriving semigroup or deriving monoid for status, and then there is some generic default that is going to be filled in. But there is still a way, or there are actually multiple ways, and that's part of the point, to come up with such an instance. So, for example, we could, I mean, semigroup is about finding an associative binary operator, right, that combines two, in this case, elements of type status and gives us a new status. So we have at least these options. We could always choose the first of the two. We could always choose the second of the two. Or we could always take the worst status. If we imagine green is everything's okay, yellow is okay, just there's this minor problems, red is it's really bad. So we want to, so if we combine different status reports, always take the worst one. So we have a choice. But it would be nice if we could just write this down. So with deriving via, we can do this. We can derive semigroup, and we can say via first status. And that'll give us the semigroup instance that always takes the first of the two things. We can say last status, and that'll give us the semigroup instance that always takes the last of the two things. Or we can say max status, and that'll give us the one that always takes the worst of the two things. And the max status one will actually only work. I mean, so first and last is something you can always do, right? I mean, if you have two values of an arbitrary data type, you can always choose the first. But in order to do this max one, it actually relies on the fact that we already have an ORD instance, right? So you can imagine that there is some implicit rule that says if we have an ORD instance for a type A, we can produce a semigroup instance for a type A, and that we use the name max in order to refer to this rule or to invoke this rule. Right? That's an intuition you can apply. Okay, so and then you can go on and say, like via the same name, you can actually say, I don't just want to have semigroup, I also want monoid. And in this case, it doesn't just rely on the ORD instance, but it also relies on the bounded instance that we have derived, because monoid, in addition to semigroup, needs a neutral element for this binary associative operator. And if we want to do the maximum, we basically need to have bounds so that we can pick the lower bound as a neutral element, right? So there is another implicit rule, max A, that says if we have an ORD A and a bounded A instance, we can produce a monoid instance. Okay, so this is the essence of deriving via. So what does it do as a language extension? You can give names to instance rules somehow, right? If we have rules such as if there's always a monoid instance if we have an ORD instance and a bounded instance, something like that. And then you can apply named instance rules in via clauses in order to derive instances. And how does it work? So it's really not very deep, actually. So that's one of the nice things, that we are reusing existing features. So you use new types and instances on new types in order to do this naming and describing instance rules. Right? That is something that you or a library author have to do. Right? And then in order to invoke them, you just write down these via clauses. But, sorry. And then the compiler applies safe coercions between representationally equal types to get the instances. Okay, so that is another feature that is already in the compiler that is reused. Okay, so let's look at this in a little bit more detail. So we had these two rules before. So in order to describe these rules yourself, you would have to define a new type, max A, that is simply a wrapper around a value of type A. And in fact, this is already there in data.semigroup in base. So in this particular case, you don't have to do anything. You really can just use it. And then you define instances matching the rules, but for this new type. Right? So you're saying, whenever I have an ORD instance, I can turn it into a semigroup instance for max of A. And then you write the rule down, and it looks very natural, except for the mildly annoying fact that you have to wrap and unwrap this max constructor here. Right? So you might wonder why we cannot just write instance ORD A semigroup A. Right? But if you think about it, that is legal Haskell, but it's not particularly useful in practice, because the way that instance search in Haskell works, it then says, okay, this instance matches any potential semigroup instance, right? It's overlapping with anything that you ever define for a semigroup. And then you have overlapping instances, or if you have multiple rules to form semigroups, you don't have any way to distinguish them or select one over the other. So the key insight here is that by using these new types, we can give names to different rules, and then we can reuse these names in order to select the rules in the via clauses. Similarly, for the monoid one, we can write this rule down as an instance declaration that from an ORed and a bounded instance gives us a monoid instance. Okay. So if we go back to our status data type, and we wonder what does it actually do. So if we write down deriving semigroup via max status, what does GHC actually do in the background? Then the instance that is actually being generated looks like this. So it derives an instance for semigroup on status, and the method definition for the binary associative operator is just an application of the binary associative operator, but it's coerced from the type max status to max status to max status to the type status to status to status. In case you haven't seen this syntax before, this is type applications, a relatively recent addition to GHC as well, but in this case it's only used internally. So this is just saying at which type we're going to use the coerce function. And the coerce function is also like existing in GHC already, and it gives you a safe coercion between types that are known to be representationally equal, so it has the type coercible AB, double arrow A to B. And new types have the property from the very beginning. I mean, they have been added to Haskell for the very reason that you wanted to have a way to create a new data type that is distinct for the type checker, but that is guaranteed to have the same representation as the wrapped type. So whenever you have one type that is a new type of another, then the wrapped type and the wrapper type are guaranteed to have the same representation and are guaranteed to be coercible. So coercible is not a normal type class in the sense that you can define your own instances for it, but it's completely managed by GHC, and GHC decides which types are coercible. But it is clever about it in the sense that it automatically recognizes that if status and max status have the same representation, then, for example, also these two function types must have the same representation, so they're directly coercible into each other. So but that makes the actual work of the compiler in the deriving via case relatively small, because you simply have to write this instance that is full of coercions. Okay? So let me just briefly also show that it actually works. So let's go here where I have this type, and let me add deriving semigroup. Yeah, let's first do just semigroup via max status. Right, and then it will actually correctly complain in this case that I don't have an ORed instance, right? Which is correct. I mean, it'll try to apply this, but the rule says for max status, I can derive a semigroup instance if I have an ORed instance, and I haven't got one. So if I add this one, then it works. And then I can see whether it actually behaves as expected. So if I do something like yellow, red, then it should give me always the worst. Okay? So, are there any questions about this? Yes?
Why do you have to say max status? Why not just max?
Okay, the question is, why do I have to say max status and not just max? It's a good question. The reason is, while it is a little bit more to write here, it actually gives you a lot of flexibility, as we hopefully will see in a couple of the other examples I'm going to show, because you cannot just write status there. You could write something else, right? So, but it's a good point, and I'll try to get back to this. Are there further questions at this point? Yeah?
Can I write my own instance of coerce to use an instance from another type that is not automatically coercible?
The question is, can you write your own instances of coerce in order to explain to GHC that two types might be coercible where GHC isn't somehow clever enough to see it itself? No, you cannot currently do that, but you can write other type classes that are similar to coerce, but then they are also not quite as convenient to use. There is a sort of gradual decline there, but you can still do quite a lot. Okay, I think there was one third question somewhere.
Maybe this is addressed later, but when you do deriving via first or last,
Yes.
how do you coerce the maybe into, like, it'll be a maybe status inside, right? So how would that coerce work?
So if I haven't done a mistake, at least, you'll see that the example I've given for first and last did only derive semigroup, but not monoid.
Right.
And first and last for semigroup doesn't need the maybe, because you don't have a neutral element. You can simply take the first and the last. And there are actually two different new type wrappers in base these days.
Oh, right, okay.
First and the last in the data.semigroup library that doesn't use the maybe, and the first and the last in the monoid module, which does use the maybe.
Okay, that makes perfect sense. Thanks.
Okay. Right. Good. So what has changed now? So this is sort of the intermediate summary. So first of all, we're getting rid of a lot of boilerplate code, right? So we can derive a whole lot more instances simply by writing a deriving via clause rather than writing an explicit instance declaration. So, and this is in particular paying off when classes have many methods, right? I mean, in the semigroup case, it basically, I mean, actually it has like s times and s concat or something like that as well. But in principle, basically, semigroup has only one proper method. But sometimes, for example, the num class or something like that has all sorts of methods, right? And if you would imagine, you can, if you have a single method, you can still write an instance declaration mapping the single method to an implementation. That's not too much work. But if you have a large class with many correlated functions, then you can just replace the whole instance with a single deriving via clause that gives you a lot. And the other case is, like as we've already seen partially, if you can derive several instances at once via the same new type, that also saves you a whole lot, right? Because you, rather than having to write several instances which map their methods to something, you can simply derive them all at once. So that's good. The other thing is that you're now actually encouraged to write down instance rules and give them names in your modules. I think that's a good thing, because previously you could write them down under certain circumstances, but certainly not in the most direct form, because as I already explained, then they would be overlapping with everything. And if you declare new type wrappers, if you did that before, they're only mildly useful. In some cases they are, in other cases they are not very much. But now there is a real motivation for people to write down known rules to construct some instances out of others. And that's already happening. So you're seeing all over Hackage pop up things like, oh, this new type wrapper is intended for use with deriving via. And it's very nice to see. So in a way that means people are conveying more information, right? Because these rules are explicitly stated. And then the dual of that is you can justify your instances, right? So it's there's more explanation in the fact if you're saying this instance on this data type comes from the invocation of this general principle, rather than if you write down all the method definitions by hand and people have to infer that or recover that, right, and see that you haven't made a mistake. So in this case, you're programming your instances at a higher level, right? I think that's a good thing. Okay, so in the remaining time, I want to look at more examples and see that despite the fact that it's all very simple, you can do some very cool things with it. So first of all, that's not spectacular, but it's good to realize this. So generalized new type deriving is actually a special case of deriving via, and it could be completely replaced by deriving via, because the only constraint that is here, and this is like partially referring back to the question before, the only constraint here is that the type listed after via must be representationally equal to the type that we're currently deriving for, right? But it doesn't have to be in the same direction, right? So before we had a data type, the status data type, and we derived an instance via a new type wrapped version of that data type, right? And the new type wrapped version of the status data type is representationally equal to status. But in generalized new type deriving, you're doing it the other way around, right? So you are deriving for a new type using the representationally equal inner type. But both directions work. Both are representationally equal, so you can derive all these instances, right? And if you think about it, if you can apply this both ways around, you can also apply something that mentions multiple new types, right? If you wrap something in a new type and wrap something in another new type, then it's still representationally equal to the inner thing, right? And that opens up all sorts of interesting possibilities. And that is part of the reason why we require to write out the full type rather than limit ourselves to a single constructor, right? Okay, so then another interesting case that is covered here is that we all know that monads are always applicative functors. These days, applicative functors are a superclass of monads, and functors are a superclass of applicative functors. And that means that if you want to define a monad instance, you first have to define a functor instance, and then you have to define an applicative instance, and then you have to define a monad instance. Even though if you have given a definition for return and for bind, all the other things are in principle clear, right? And at least as long as monad of no return is not implemented, because then return gets out of the monad class and it's no longer so easy to specify this. But if we assume monad has return and bind, we can define a new type wrapper from monad that wraps something of type M of A. And then we can say that every monad is also a functor, because this is how we can implement fmap in terms of the monadic operators. And every monad is also an applicative, because this is how we can implement pure. Pure is just return, right? And this is how we can implement star. There is either the app operator in the library somewhere, but then you have to watch out whether app is still defined with a monad constraint or has been simplified to work with, or you can like write it out with bind and return, and then you're sure that you're really using the monadic interface, okay? And then I'm using a standard data type here, but really you could imagine this is your own new data type for which you are just interested to define a monad instance. So you define a monad instance and just the monad instance, and you're deriving the functor and applicative instance via the monad instance, and you get them for free, okay? So now let's look at a number of other interesting examples. So this is an event type that reuses the status type that I've been talking about in the beginning. And it's an example of a type that you're sometimes dealing with, which has like a record type, has a bunch of fields, and some of them are rather well behaved, like status, and others might be kind of ugly, like I/O actions or functions or stuff like that, right? And as soon as you have a record that involves a function type or an I/O action, all sorts of things become very difficult, right? I mean, you can no longer easily get an equality instance, you can no longer easily get a show instance, you can no longer easily get an ORD instance, and so on and so forth. But perhaps I'm not even interested in this part, right? Perhaps I want to only use the status, right? So there are different variants or aspects how you can deal with this, but here's one thing you can do using deriving via. So you can first derive generic for it again. And then you can say, OK, I want to derive EQ for this type using just the status field. Right? And that'll say, OK, if there is a status field in this, first, this has to be a record, it has to have a status field that has this name, and there has to be an equality instance available for the status field. But if these conditions are fulfilled, I get an equality instance for the event type, right? And how does this work? This uses the generic lens library again internally, so it's right. But so you create a new type wrapper field that is parameterized over a type level string, so a symbol and a type, but it still wraps something only of type A. And I'll get back to this in a moment. And then you're saying, OK, if you have a has field instance, and this comes from the generic lens library, that for the name A has a field of type B in the large type A, and if there is an equality instance for this type of the field, then I can define an equality for the wrapped type simply by limiting the equality to that field. Okay, and get field, again with a type application, is another function that comes from generic lens. Okay. So the interesting thing here is that we get a lot more power because we can add these extra arguments to our new type wrappers. Right? So even though we are wrapping something of type A, and it's still representationally equal to type A, we can pass in extra parameters to what we want to do. In this case, it's just a field name, but you could do arbitrarily complicated things, right? So you can give all sorts of extra descriptions of what you actually want to do, and these extra descriptions, they can then be used in the instance declarations, right? So that's a very interesting thing. And one more example I have is that's something that actually I wanted in similar ways a long time before deriving via was done. So I said in the beginning, deriving from JSON into JSON, what does it do actually? For some type, it will give us just strings, right? So it'll, if we turn the status green to JSON, we'll get a JSON string that is contains the capitalized word green, right? But now, for example, this artifact that the constructor names are capitalized is a typical Haskell thing, and we might already have an existing JSON model somewhere that says, OK, green is just written G, or something like that, or corresponds to the number 0, or I don't know. And so we might want to have something different, right? And that applies a lot. Often you want to have different external representations that perhaps all use the same external name and are compatible with each other and are guaranteed to work with each other, but for some reason that external name doesn't match the internal name. So with deriving via, you can do something like this, right? And this is again using the same splice in extra external information trick. So you derive a custom enum new type wrapper that wraps a type level list of strings and something of type status. And it's still representationally equal to status, right? So we can derive something for type status via it. And what it does, it's basically replacing the constructor names by the ones in the type level list, right? And it will actually give you an error message if you are not putting exactly the right number of strings in here, right? If you put too few strings in there, you'll get an error message if you put too many in there. You can argue, okay, it's still possible to accidentally flip them, but they're close to each other, and you could even like fix that, but then you would probably have to repeat the other name and say, I want to map capital green to lowercase green or something like that. So, but I mean, there's a lot of flexibility there, right? And how does that work in principle? So the idea here is to use generic, I mean, from JSON and to JSON already use generic programming, in this case GHC generics. So GHC generics works with a representation of the data type. So if I ask here, using GHC's very memorable syntax for expanding type families, what is the representation of status? All right, you'll get this horribly large thing, which is perhaps not even all that easy to read on the black background, but perhaps I can at least highlight this. All right, you see it's a data type, and then there is the name of the data type there, and then it's a choice between ultimately 3 constructors, and the first constructor is called green, and the second constructor is called yellow, and the third constructor is called red. Right? And now I can do, I have a version that is called rep prime, and rep prime, let me again scroll this up, takes a type and a list of symbols, and it's actually implemented in terms of something yet more complicated. Right? And if I do rep prime of status, and I give it a list of symbols, so let's say just G and Y and R. Oh, and I need to enable data kinds in my module. Then you'll see I get back a representation that looks just like before, but the names of the constructors have been replaced by G and Y and R. And now I can use the same generic algorithm as was used before, but it will automatically fill in the other constructor names at the right points, okay? So that's the basic trick there. Okay, so
Can I ask a quick question?
Yeah,
Can we
absolutely.
just, for interest, can I see what happens if you don't have 3 elements in that rep prime, though?
Yeah,
What
I
does it
mean,
say?
this is something I set up for the talk only, so I didn't go to endless lengths. But I mean, you can use the type error feature. So actually, so I'm not getting it to trigger right now. Let me see. So I have in my demo file somewhere. So this is the definition, actually. I don't want to really show this. But here, I have an instance that says mod generic status and GYR, right? And if I don't put the right number of elements here. So this is something that I use to test. Then I get too few labels, but I could put in yet more explanatory error message that repeats the labels that I've given and how many constructors are expected or something like that. And if I put too many, I also get a similar message, and I get too many labels. Okay, right. Yes, so actually this is already the end. The conclusions of this are, so deriving via is available right now. It's available in GHC 861. So thanks to primarily the hard work of Ryan, who did all the implementation work. And it's a very lightweight feature in terms of reusing existing language concepts. And it generalizes a lot of stuff, which is nice. So it generalizes generalized new type deriving, and it actually, to some extent, also replaces default signatures. Because if you think about it, type classes currently can have the generic defaults, but they're a little bit ugly, because you have to define a generic default at the moment you define the type class, and you have to commit to one blessed way of generically deriving this thing, even though there might be multiple different generic programming libraries or multiple slightly different algorithms, and there might be performance concerns, or there might be different subclasses of data types for which you can do something better. All these kinds of issues, and having one generic default is like kind of unsatisfactory. But with deriving via, you don't need generic defaults anymore. You can write down your rule in a different module, right, that is far away from where the type class is defined, and you might come up with a way to construct instances of that type class that wasn't even known by the original package author, and you can still use this, right? So so you can, in principle, get rid of the need of most default signatures. And then the other important realization is really that, like, I mean, deriving via is already nice to have for the simple cases, but the real fun starts once you actually consider that you can splice in extra information, you can parameterize your rules, you can chain rules, you can compose multiple new types together. A very nice example is this capabilities library for which there was just a blog post by Twig.io. They use deriving via in ways where they actually chain 5 rule applications together and things like that. So that's very nice. Okay, that's what I wanted to say. Thank you.